Thank you for amazing introduction, and hey everyone. So yes, my name is Mikołaj, and I work as a senior software engineer, or front-end engineer to be specific, at this company that you might have heard about today, Virtus Lab. And I would like to start my presentation with a question for you. Do you know what front-end developers like doing the most? Any ideas? It seems that we love to create NPM packages. And maybe that would explain why we have over 2 million entries in the NPM package registry. And there are around 1,000 new packages added each day on average, which is completely insane. So, well, I didn't want to miss out on all the fun. So together with my colleague, we created our very own open source project and published it as an NPM package. And I would like to tell you more about this because, well, I think there is something to be learned from this story. So let's start from the beginning. In order to create some kind of NPM package, we need some idea. And I happen to have an idea. I wanted to create a package for dealing with forms in React. Okay, you might be wondering, why do we even need a package for that? Here is a visual explanation. Okay, a bit more serious note, however, creating complex form on the UI can be somewhat painful, so it does make sense to create a library for this. Okay, but we have another problem. Turns out other people had that idea long before us. This graph shows popularity of some of the most relevant React form libraries. The number one at the time being the blue line, Formic. And well, I happen to actually use Formic in one of my projects, and I was not very satisfied with it. I felt like there's a lot of space for improvement. And my two main gripes with it was that it had rather poor integration with TypeScript, and it had questionable performance. I will talk more about this later, but interestingly, there seemed to be no good solution out there which focuses on delivering great TypeScript integration. And this is perfect. Let there be yet another NPM package just to fix this. All right, we named our project Forms, as in Form.ts, and we set out a couple of simple goals for it, as you can see here. We even managed to secure some funding for the project from Virtus Lab research and development budget. Awesome. So now we have all that we need. It is time to start coding. Oops. So how did it go? Well, it turns out that creating a form library from scratch is not exactly an easy task. And I would like to dive into the details of why. Our first major challenge that we had to overcome is the API design. Now, what I understand as a good API for a library is one that maximizes developer experience and type safety. The latter being the focus of our project, its selling point, basically, so it's rather important. Well, luckily, we had some idea how to approach this. We followed this process, which can be called API-first design or API-first approach to software development, where we put the API at the first place in a way that the API should drive the implementation rather than implementation shaping the API. So let me demonstrate on a very simple example. Let's say we are creating a very simple counter package. So what we start with is any, the dreaded any type. And once we have that, we can use our imagination, just kind of explore what kind of an API would be best for counting, in this case anyway. And once we have that, the next step is to verify if the API we just invented is possible to represent in our type system. So for the counter, we could create a stub class like here. And so yes, it's pretty trivial, but it doesn't have to be. In our case, we actually had some problems at this stage. because we invented a pretty complex API, which didn't really work with TypeScript type system. But let's say we managed to figure out the API that we want. So the next logical step is to create specification, because it kind of works with test-driven development. It makes sense at this point to write the test, as we have the stubs and we have the types for our API. It should be easier. And of course, finally, we fill in the implementation. And as you might imagine, each step would get much more interesting if you work on something more complex like we did. And I can generally recommend this approach whenever you're creating something from scratch and don't know how it should look like. Okay, but back to our project. Where did this lead us? So first of all, it led us to enforcing a statically defined schema for our form. And what I mean as a schema is a single source of truth for information in compile time and for information in runtime. It looks like this. So as you can see, the schema tells us what form fields there are and what are their types. Why do we need it? Well, this will allow the users of our API to reference the fields of the form in order to interact with them. And at the same time, it enables the propagation of type information. And this example should demonstrate it. So let's say we are the user of our library and we want to, for example, render an input for the city field. So the first thing we would do is to use the schema to get this field descriptor object pointing to this field. And as you can see, this object carries the string type information, which will be used later. So in the next step, we pass this field descriptor object to one of the functions exposed from our API. In this case, it's this useField hook, which I will get back to later. And as a result, the user can now do stuff like get the value of the field and set its value and so on. And everything is properly typed, which is good. Okay, let's go back to forming. So the forming has a different approach, and in fact, pretty much any other form library had a similar approach to forming in that we don't have a schema, so the API is more dynamic, and we reference the form fields via string keys. Now, as you might imagine, referencing or basing the API on strings can have some limitations, and in this case, the users would be forced to pass around the types manually in order to get the API typed, or they would have to deal with a lack of types. But there's actually a trade-off here, because on one side we have less type safety, but we also have dynamic form building, so the API is more flexible, as opposed to our API, which offers greater type safety at the cost of flexibility. And the reason I wanted to point this out is because this trade-off between static and dynamic APIs is not really specific to form library. It's something that can be found in other places as well. All right, so that's in a nutshell how our schema-based API works. The next thing we did in terms of optimizing our API design is related to encapsulation. And for that purpose, we use nominal and opaque types. And I would like to tell you about them and how we can use them in TypeScript. But first, we need to discuss structural typing. So as you might know, TypeScript uses structural typing, or is based on structural typing. This means that when the TypeScript compiler tries to compare two types and decide if they are compatible with each other, it actually looks at the structure of the types. And how this works, you can see on this example. So let's say we have this useField function which accepts this field descriptor object or objects of this type. So our intention is that we provide the user with these with objects of this type from the schema, and the user should pass them in. However, as a natural consequence of structural typing, it's possible for the user to actually pass in anything that has compatible underlying structure. In nominal typing, however, which is a different approach to structural typing, and languages such as Java, for example, rely on nominal typing, this would not be possible. We would get a compile error. And why would we want that? Well, it turns out that it can be desirable because this is not the way we intend our users to interact with the API. So if we block it at the compile, on the compile time, then, well, it will kind of transfer to a better developer experience. It will guide the users towards the intended path, basically. Okay, but I mentioned TypeScript uses structural typing. Turns out there's a fairly simple trick to replicate the nominal typing in TypeScript. We can do it using the private class fields for tagging our types. All we need to do is to intersect our type with this nominal util class. And this will result in the compile error. This is kind of nice, but we can go one step further, and we can use opaque types in order to hide our implementation details. So to make this field descriptor type that we have created opaque, we just need to export it as an empty nominal type. And we also need a second internal type which contains the actual structure. And well, this will kind of break our implementation, so we will need to convert back and forth between those two types. For that purpose, we can create two simple helper functions. And the result is that the TypeScript will prevent our users from seeing what's inside this field descriptor type or accessing it. And this translates to better developer experience because these internal details will not be polluting the IDE of the completion. And of course, there's a general benefit from encapsulation because now we can change our implementation details without breaking the code of our users. Okay, so as you can see, the opaque types is a pretty useful concept. Unfortunately, they're a rare sight in TypeScript code bases. They can be found, however, as a native feature in many languages related to functional programming, such as Scala, for example. So we can consider using them whenever you need to encapsulate stuff. Okay, so that was me rambling about our API design. But let me move to the next challenge that we faced in terms of optimizing the performance of the library that we are building. Okay, so I mentioned that I had an issue with the way Formic dealt with this issue with performance. What I mean is that anytime you change the state of the form, it will cause the entire UI to re-render. And this is the most common performance issue found in React applications. As you might imagine, it can lead to significantly slowing down the application if the UI is very complex. And we have an idea how to solve this. We will need an internal state management solution for our library, though. Why? Well, React does not provide one that is good enough, and we also have this goal of having zero dependencies. And this presents us with a perfect opportunity to explore atoms. Okay, so let me talk about atoms. Atom is a simple concept. It's just a container for mutable value, and it also implements the observer pattern. In other words, it can be called a unit of reactive state. And I would like to walk you through a simple atom implementation just to show you how cool the atoms are. So what we start with is this, a value and a setter for the value. And we can implement it like this. That's probably the simplest way. We just have a function returning our atom object, and we keep the state in the function closure. Okay, so now we have value, we have setter. The next step is to make the atom observable, and for that purpose, we will need to add a subscribe function. And to implement it, first we need array of subscribers stored in our state. Second, whenever the value is updated, we will need to notify every subscriber. And lastly, the subscribe method itself is straightforward. All we need is to push to the array of subscribers. And well, we missed one thing, because if we can subscribe, we also need to be able to unsubscribe. This can be done like so. So we return another function from the subscribe function. Okay, so this brings us to a complete implementation of a very simple atom, which can be used for state management. I will try to show you later how is it exactly useful for us. But for now, let's see how can we integrate it with React, because after all, we're making a library for React. And well, one way to do it is use the built-in React hooks, as presented here, to subscribe to the atom and then unsubscribe from it, while also forcing the component to re-render every time the atom changes. But this is actually no longer the valid approach, because with the introduction of React 18 and its concurrent rendering mode, there can be issues with the synchronization of state known as tearing. So we need to use a special hook provided by React called using external store. But that's just an implementation detail. Well, we are still missing something important, though. Because our initial goal was to be able to selectively re-render our components whenever the relevant piece of state changes. And in order to achieve that, we want the atoms to be decomposable. And the way to achieve that, at least for us, was to use lenses. Okay, let me briefly talk about lenses as a side discussion from the atoms. So the lens, just like atom, is a simple concept, at least at its core. It's just a pair of getter and setter functions that operate on some data structure, on some objects. It can look like that when defined in TypeScript. So let's see that on an example. The first thing we need is some kind of data structure to work with. And I'm going to use the one that I showed before on the schema. We have a form object containing an address object, and inside it is a city string. Looks like this. So the next thing, let's say we want to operate on the form.address.city property using our lens. So we can create it like this. First, we have a getter, which is trivial, and then we have a setter. Now, the setter does not mutate the object, the input, but rather it returns a copy of it with the value updated. The reason for that is that lenses are a concept from functional programming, and as such operate on immutable data structures. And there's benefit to using immutable data structures. We can easily compare two versions of an object and determine if they were changed, because all we need to do is compare their reference. Okay, so now that we have our lens, we can use it to get the city out of our form, or we can update the form by creating a copy of it. This is not good enough, though. What we want is to be able to create simple lenses via some helper functions and then compose them together into a more complex lens operating on the data structures that we are dealing with. We could do it like so. And let me quickly show the implementation. It's not difficult. First, the identity lens. The identity lens doesn't actually do anything. We only need it as a starting point for the composition. And then the prop function, if we go back a bit, is actually the same code as this custom lens that we have made. The only difference being that it's wrapped in a generic function. So it looks like this. All right. Now, the final thing we need is the compose function. And this is when things get a little bit more interesting. So the function itself is kind of simple, but at the same time, it's difficult to wrap your head around it, I think. But what we can do is take a look at the type signature, because it tells us the entire story. When we have two lenses which are compatible with each other, we can combine them together to get a single lens. And this works exactly the same way as function composition. When you have a function which outputs a type that can be fed into an other function as an input, then we can combine the two functions together via function composition. Okay, so let's assume this code works. I recommend implementing this as an exercise. The next thing, we can discover that if we can compose two lenses together, we can actually compose any number of lenses together. All we need is to throw them into the array reduce function using our binary composition function. Okay, so I would like to end this quick digression on lenses by talking briefly about the existing lenses libraries. Because what we have done is much simpler than what is offered out there. It's just sufficient for our purposes. Basically, what I showed you is functioning, but it's just the tip of an iceberg. So what I recommend is that if you ever find yourself dealing with complex immutable data structures, then chances are that you will find the lenses useful. And as you can see, there are many libraries. What I recommend is checking out the calm.js repository, as it has very verbose documentation on this subject. Okay, let's go back to our atoms. How do we combine the concept of an atom with the concept of a lens? What I mentioned earlier is that we want the atoms to be decomposable. What do I mean? Well, given an atom, we can create a second derived atom from it via the lens. And the resulting atom will hold some smaller piece of the state than the source atom, which is basically what decompose means. Also, changes made to any of these connected atoms will be instantly reflected in the other one. It reminds me a bit of quantum entanglement. Let's see this on an example. So first we need some kind of source atom. So let's say we have an atom holding our form values, this object that we worked with previously. And we also take the city lens from the previous example. Now, as a fun fact, we already implemented both of these. You know how to create them. What I want to show is the atom.entangle function, as it's a tiny bit more complicated. But what it does is that it accepts an atom, a compatible lens, and outputs this entangled atom. This atom will have the relevant value, and the value will also be updated as the source atom changes. But it's also a regular atom, so we can subscribe to its changes. We can set its value, and again, the value will be updated on the source atom. So it works both ways. And let's go back to our library. So how do we benefit from these atoms and these lenses? Basically have a simple atom library and a simple lens library inside of our form library at this point. Well, it turns out that lenses work very well with our form schema builder that I showed before. So when creating the schema, we can also create lens for each field as we go. And then the resulting lens can be stored in those field descriptor objects. And for that purpose, we just need to use these lens prop and lens compose functions that we have also already implemented. Okay, so now let's take a closer look at what happens in the use field hook that is used for interacting with field that I showed before. And in a simplified version, at least it's very similar to this example from before. So what we want to do is you want to create this entangled atom which focuses down on the relevant state, the state of the form which is relevant for our field. And we can access the general form state, which is basically a set of atoms. And we also have the length from the schema, as I showed you just before. So then we can get our entangled atom, which is containing specifically the things that we care about. So when we subscribe to this atom inside our React component, this will bring us finally to the thing that we wanted. We will get this performance optimization. The component will only re-render when the relevant piece of state changes. And as a bonus, we also get a pretty interesting and elegant way to manage our state. So now, I showed this example before when talking about forming, but now when the user types in one input, it does not cause the entire UI to re-render. Okay, so that's how we achieve this performance optimization. Of course, this is not solving all of our issues, we just solve the most pressing issue. And atoms, just like lenses, are a topic I only scratch the surface of. And what they do, however, is they can provide an alternative approach to managing the state of your application. And this actually gained quite a bit of popularity recently. So if you are interested in learning more, I recommend to check out the Jotai, Recoil, or Kefir Atom packages. Okay, as we are nearing the end of this presentation, let's talk about the last final challenge we faced, which is different because it's of psychological rather than technical nature. So take a look at this graph. What it shows us is the history of contributions to our projects in terms of lines of code added, at least. And it tells us a story. So did we manage to finish our work in the first 7 or so months and then move on with our life because we are very happy with what we have accomplished? Well, unfortunately, not quite. So what actually happened is that we did manage to create a working library with most of the planned features in place, but at the same time it became apparent that the API we had so carefully crafted has some flaws. And I couldn't figure out how to fix those flaws, while I also wanted to deliver a perfect 1.0 release. And this is the result of this sort of thinking. We ended up doing nothing, at least for quite a while. So did we abandon the project? Fortunately not, because what actually happened in the meantime is that we got some real users using our project. And we got some feedback from them. And the feedback was mostly positive. They were rather satisfied with their experience. They had some feature requests. They had some complaints. But they didn't seem to be particularly bothered by the flaws that bothered me in particular. And this helped me change my attitude a bit. This motivated me to get back to work on this project. And what I realized is that we need to finish what we have started because it already provides good value. Of course, after that, we can continue to improve it. If you want to learn more about this project, I recommend you check out our GitHub page. All right, so what can we learn from this? Well, first, I learned that API design is a really hard problem. So you need to put a lot of thought and effort into it from the very beginning. And even then, you kind of need to be prepared that it might just kind of go wrong, because it's hard to predict everything. And the second thing, which can be a bit controversial, is that you can learn a lot of things by creating various solutions from the scratch. And what this means is that in some circumstances, it can be beneficial to reinvent the wheel, like we did there. There were existing packages for atoms, lenses, but we didn't use them. And next, this one is obvious. User feedback is awesome. It's a great motivation when working on an open source project. But what I do recommend is try to get the feedback from your users as soon as possible. It will help. And finally, it's always better to finish an imperfect project rather than leaving it for later and waiting for some divine inspiration to come and enlighten us. It probably won't happen. Okay, so that's basically it from me. Do you have any questions?
Yeah, I think we have time for one question. Yeah, here it is.
Hi. Okay, hi.
Hi.
I have one question because you spoke mostly about the inner workings in the code, but I'm really interested how you work for these 2 years. Like, how much time did you spend? How you collaborated with the second person, right? The second person.
Yeah.
What was your how you track progress? How you define your priorities and so on.
Okay, so basically this was kind of a side project for us. We did it mostly in our free time, although we were paid for a little bit to kickstart it. So it worked for us as a side project. We worked for it whenever we had some time. And of course, at the beginning we had the most motivation, so we had some quite consistent pace, like you can see here. And the way we organized, well, we had created some spreadsheet document with a little bit of roadmap. The roadmap was actually planned for 5 weeks of development, which stretched out to 7 months and then to 2 years. But it was kind of helpful at the time. And for other things, we just use GitHub. GitHub issues work pretty well. So I hope that answers the question.
Yeah, thanks.
Thank you.
All right. Thank you. Hopefully that helped to cure your perfectionism, at least to some
I
extent.
think it did, yes. That's the lesson.
Thank you.
Thanks.